introduction. Thank you for the invitation. Let me try to share the screen.
Okay. Great.
Here it is.
Yes, go ahead, please.
So since it's a seminar, please feel free to interrupt me and ask questions if you like. The title of today's talk is Continuous Learning for Android Malware Detection. This was work done during my postdoc with my co-authors Zhou Jie and David from Berkeley. This paper was just accepted at Yizheng Security and it will appear at the symposium. So when we started looking at this problem, we were asking the question, is Android malware detection already a solved problem? You can do things like take 1 year worth of Android malware apps and some benign apps, train a linear SVM to predict whether an app is benign or malicious. If you do that based on sort of a random split of trained test data, which would give you roughly similar test data distribution and training data distribution, that will give you a model with about 99% accuracy and only 0.4% false positive rate. So these numbers are really good. And it makes you feel like maybe there isn't much work to do. Android malware detection is already solved. However, as demonstrated by many recent papers, we shouldn't just do a random trained test data split. One problem for malware detection is what if we evaluate on test data distribution that is different from training data time? So here we tried this. We trained on 1 year worth of data from 2012, and then we test on future data, newer data every month following up from up to 2012. As we can see from this figure, this shows the F1 score from initial training, F1 0.99, from the very left data point, over 7 years of time from 2013 to 2019. And shortly after 6 months of deploying this classifier, the F1 score already dropped to 0.77. So it doesn't really work if you want to deploy a malware classifier to test on future data. And this problem is called concept drift because there are newer malware samples and new benign sample behaviors, which are always evolving over time. Now, what do we do about concept drift? There are roughly 3 areas of research that try to address this problem recently. They are drift detection, drift adaptation, and learning robust features. So for drift detection, some recent papers include Transcend and Transcendent. So Transcend series, these 2 papers are built on the conformal prediction theory. On a high level, they want to see, given a test sample, how dissimilar the test sample is from all the known samples from each class. And if something is more dissimilar, then it might be out of distribution. So we should detect the drift. And there's also another word called CADE. CADE uses contrastive learning, which is one type of representation learning technique. So if you can learn good representation, which is good embedding features to represent inputs, then in the input space, that will allow you to see clusters of different malware families, and then out of distribution samples may be outliers. And also there are a lot of OOD detection papers for image applications, but there aren't that many work that applying these OOD detection technique for security problems. And Transcendent and CADE are probably the most relevant drift detection related works. Now, if we can detect drift, what do we do about these? There are mainly 2 types of things we can do for drift adaptation. One is to reject drifted samples, and the other is to do active learning. So the Transcend and Transcendent papers take the option to reject drifted samples If you can detect what samples have drifted, then we just don't predict them. And on the other hand, Kate tried one iteration of active learning experiment. In other words, if we detect some samples are OD, we can ask human analysts to relabel these samples, put them back in the training set, and retrain the classifier. And lastly, for learning robust features, for example, there's this one recent paper called API graph. The goal of API graph is to learn semantically similar features. One example they used is if a malware sample is doing multiple things for network connection, for example, through HTTPS, TCP, or UDP connections. In the original feature space, they may be calling different APIs, but semantically, they're doing the same things. So API graph learns what kind of input features are semantically similar and merge them into meta features. If you use meta features, they can be more robust against concept drift. So these are the rough different areas of research in this space. And in our paper, our problem is try to focus on how to do active learning more effectively to adapt to the drift over time. So this is a basic active learning setup. In our paper, we want to solve the problem of active learning. If we look at the loop from the left side, we start from an initial training set. We take that training set, we train a classifier, and the classifier can be used to predict new test samples as shown on the right side. Now, after we deploy this classifier, then we can select several new test samples for analysts to create human labels. And these newly labeled samples can be put back to the training set to expand this original training set and retrain the classifier. So this closes the loop, and we can even do multiple iterations of active learning over time. Now, there are some real-world constraints of how we may be able to practically do active learning. Mostly the constraint is for a given day or a given month, if we have access to one analyst to generate labels, the analyst has limited time, and therefore there's a fixed labeling budget we can request the analyst to do. And based on our experience and according to many related works, the state-of-the-art ways to select samples for analysts to label is called uncertainty sampling. So this is a very simple scheme, but surprisingly, uncertainty sampling is very hard to beat in practice. So what would uncertainty sampling look like in the previous experiment? Here in the figure, I'm showing two curves. One is the solid line representing the baseline binary SVM with no active learning. And second is the dashed blue line, a baseline binary SVM, but with 200 samples a month labeling budget over every month. So we select 200 most uncertain samples, give these to the analysts to take human labels, and put them back to the training set and retrain a binary SVM classifier. As we can see from the curves, just by doing uncertainty sampling, we can reduce the false negative rate from 38% to 14%. And we can improve the F1 score from 0.69 to 0.88. So uncertainty sampling seems to perform pretty well, but the F1 score is still not ideal, and the false negative rate is pretty low. Just to give everybody an idea of what 200 samples a month mean in this context, the data set we experimented with is collected by following the hashes released from the API graph paper. So we call this the API graph data set. If we allow 200 new labels per month, this is roughly 5% of new test samples a month. So it's a common setting used by related work. And this can reduce the false negative rate from 38% to 14%, given 5% labeling budget for every new test month. All right, so here's a problem that our paper tries to solve. How can we improve on top of the best baseline, including uncertainty sampling and also all the previous related work that I mentioned? And this is our overall idea. In order to do contrastive learning for Android malware detection, instead of just doing uncertainty sampling on the classifier's prediction score directly, we would like to learn a new robust representation learning to get the embedding space. And we would also like to combine that with a new uncertainty measure that will perform better than all the previous baselines. So in the slogan form, we call this, our vision for continuous learning is to combine contrastive learning plus active learning. So this is based on several recent works where we took their ideas of, it seems like self-supervised learning is better and they can deal with data distribution shift better than supervised learning. And there's also a related work, Kate, that showed us maybe if we do contrastive learning, we can detect outliers and label hard samples more effectively. So I'm gonna talk a little bit more about the details of what inspired our paper. So this is what contrastive learning can do. We're inspired by this paper called CADE from UC Security 2021, where they showed some promising early results of training a contrastive autoencoder based on 7 malware families. So if you just train this on a few malware families with roughly balanced samples, on the left side, you see that in the original feature space, there isn't much difference between how the features are clustered across different malware samples. If we do contrastive learning and learn an autoencoder, then on the right side, we can learn a very distinguishing embedding space where different malware families form clear clusters. So I wanted to note that the UMPay family was not originally in the training set. So in this example, we can see that even for a family that's not in the training set, they can form a few clusters. So that tells us the new malware family actually form very distinctive clusters that are different from samples in the training set. On the other hand, on the right side, there are some drifted samples from an existing malware family, Droid Kung Fu. So they are variants of existing families, but since these drifted samples are close by to the existing cluster, we assume that if we build classifier on this embedding space, then such classifier should be more robust against these gradual drifts. So that gives us two things. If we can learn a really good embedding space, we have the potential to find out what are the hard samples, these families of clusters that are very different from existing training data, and potentially they can be used for labeling, and we can send them for human analysts to label. And the second thing this embedding space gives us is a potential to be more robust against gradual drifts in the data. So we tried the scheme, some real-world data sets with unbalanced benign and malware family counts. And also in the real-world data set, the majority apps are benign. The original contrastive autoencoder scheme it's challenging for it to work on real-world data set because of these issues. There's imbalanced cluster, and long tail distribution of malware families. Now, when we deploy that in a real world data set, it seems like it's not that simple. It doesn't just work directly. If we train unknown families and try to detect new families. So here in this example, we have a cluster of benign samples in the embedding space and two clusters of training families, air push and fake installer. Now, when we see a new family called add mogul, some of the new family samples are like within the benign cluster, and some of them are in between the benign cluster and the malware family cluster. So that makes the classifier very likely to predict the new family as benign. So there's this challenge. So our guess is this happens because this is a base rate problem. If the majority of apps are benign, then the classifier will think it's likely to be correct if you just predict a new sample to be benign most of the time. In addition, the original contrastive learning only learns pairs of samples to be similar as long as it's either a malware family or a benign sample family. That doesn't tell you anything about how similar different malware families are compared to each other. So if there isn't a notion of we want different malware family to be more similar than they are within each other. So to deal with this problem, and we would like to learn a better embedding space, we propose this new idea called hierarchical contrastive learning. So what this does is instead of saying malware are equally as similar as benign pairs, we also want a hierarchy of even if two malware families do not share the same family label, they're still kind of equally similar as two benign samples. So here I'm showing two figures of what does it mean in the embedding space for regular contrastive learning versus hierarchical contrastive learning. So in regular contrastive learning, we can see kind of the equal distance between the three training families, benign, air push, and fake installer, because the three families are all in the same level of similarity hierarchy. But on the right side, if we do hierarchical contrastive learning, we can see that there is a larger distance between benign and the malware families, air push and fake installer. And you can still see some smaller distance between several small air push clusters and small fake installer clusters. So this means that we want a larger distance in the embedding space between benign and different malware families. But we still want some sort of different distance between different malware families. However, if some samples belong to the same malware family, we want them to be most similar. So we have these two levels of similarity hierarchy. The higher level is if any samples are malicious, and regardless of the family, we want them to be weakly similar to each other. But on the second level is if any two samples belong to the same malware family, then we want them to be strongly similar. And now this allows the embedding space to learn a weakly similar notion between different malware samples, even if it's an unseen malware family. So as we can see that in this example, when there's a new family at mogul, it just naturally joined this big cluster of malware samples on the right side. And the embedding space can tell us that the new malware family is more similar to malware samples than benign samples. So this is where we were. All right, so we want to learn a more robust representations learning. We want to propose a new robust representation learning method. and then a new uncertainty measure for active learning. So this is the first part. We learn a hierarchical contrastive classifier. Specifically, to train this classifier, we have two parts of the losses. We would like to minimize a sum of hierarchical contrastive loss and classification loss. So here we use a hyperparameter lambda to tune what is the proportion between these two loss terms. We choose lambda such that the average value of these two losses are similar. So not a single loss will dominate the learning process. This is a typical procedure in machine learning. I'm going to talk a little bit about our hierarchical contrastive loss. So we have three terms for this hierarchical contrastive loss. They capture whether any pair of sample within the batch are either weakly similar, strongly similar, or dissimilar. So for the first one, we would like to say some pairs of samples are weakly similar if they're either two benign samples or two malicious samples from different families. If they are weakly similar, then we require their distance to be smaller than a margin M. Here, M can be also a hyperparameter specified by the user, and our experience is M actually doesn't matter too much. So we just want M to kind of make different samples to have different distance. And the second term in the hierarchical contrastive loss say that some pairs of samples are strongly similar. They are actually any two malicious samples from the same family. So if they're strongly similar, we want the distance between their embeddings to be as small as possible. If there's any distance between them, then they incur a loss value. And the last term is capturing how dissimilar some pairs of samples are. If any pair of sample consists in one benign sample and one malicious sample, then this pair is dissimilar. And we want the distance between their embeddings to be as large as possible. We want the distance between them to be at least 2M. So that gives us three types of distance between weakly similar, strongly similar, and dissimilar samples. And after learning this classifier, we can put that into the active learning procedure. And also when we learn the hierarchical contrastive classifier, we have some encoding layers. And then the hierarchical contrastive loss is given on the embedding space before the classification layers. Now, in the active learning procedure, instead of doing this loop of train, predict, select, expand the training set and retrain the classifier, we replace the classifier with our hierarchical contrastive classifier, where we actually have the embedding space that can learn to distinguish between different kinds of similarity. So the next question is, how can we select samples when we see new samples at test time? So here we propose a new uncertainty measure that will allow us to do this. Why do we need a new uncertainty measure? The challenge of doing uncertainty sampling for contrastive learning is there is no previous uncertainty measure for contrastive learning. If we think about any kind of uncertainty for classification, to compute an uncertainty measure for a classifier, basically you only need one input and it's predicted label. It doesn't depend on anything else. However, when we train a contrastive encoder, or if we do any kinds of contrastive learning, you require the similarity measure between a single input and other inputs. So it depends on multiple input. You cannot just take one input and its predicted label and compute the uncertainty. So we designed this new uncertainty measure based on two key ideas. One key idea is, what if we take an unsupervised learning view of a traditional uncertainty measure of a classifier? So we did some calculation in the paper that you can actually see the uncertainty of a classifier as you just compute the classification loss of inputs and its predicted label. So the key here is usually we take the inputs and you will already get what is the prediction probability of the classifier that tells you the uncertainty of classifier. But now we also care about what is the predicted label. And if we have the predicted label and put this back to the original training loss, that is actually equivalent to the uncertainty of the classifier. Now, the actual value of this uncertainty measure where we plug in the predicted label may not be exactly the same, but that will actually give you the same order of how you rank which sample is more uncertain than the other. Since here we take the predicted label, this is an unsupervised learning view, and you only need the training loss to compute the uncertainty. And given this, we can actually apply this unsupervised learning view on the contrastive loss. Since we train a hierarchical contrastive classifier, that will also give us the predicted label of a given input. And then we can put that back into the training loss. And the large loss value will mean some similar samples are far apart, so nearby this training sample, or some different samples are close by. By similar, we mean maybe that the samples are from the same malware family. By different, we mean maybe it's benign and malicious samples, but they are really close in the embedding space, so they would have a high contrastive loss. So more concretely, this is our new idea for a new sample selector, which we call the pseudo loss sample selector. The name comes from, we take the predicted label as a pseudo label and put that back into the training loss. So once we have trained a hierarchical contrastive classifier, at test time, we're seeing new test samples as incoming samples. We compute the predicted labels from these test samples. And what we care about is, given a test sample, we find the nearest training samples with their ground truth labels. And we form a batch of one test samples with remaining training samples. So we have one predicted label and all the remaining labels are ground truth labels for the training samples. And that allows you to compute the loss of that test sample. And we can repeat this procedure and compute the loss of all the new test samples. That gives us the pseudo loss values, which is the uncertainty measure in our scheme. And then we can rank these new test samples based on the pseudo loss values. The ones with higher pseudo loss values are the most uncertain samples, which we can select them and give analyst labels. So we would put these most uncertain samples with analyst labels back into the training set and reaching a classifier in the active learning procedure. So I've just told you about how we designed our new hierarchical contrastive classifier. And on top of that, how we can use a new pseudo loss sample selector to do continuous learning for Android malware detection. So this is how we realize our vision of doing a combination of a contrastive learning and active learning. Before I talk about some highlight of experiment results, is there any question?
Right, so we have one question from Yizheng.
Hi. I have a question regarding the hierarchical constructive loss. So Yeah, you have mentioned that the loss combined by the dissimilar loss, right? So you need to enlarge this distance, dissimilar distance. So my question here is how you make sure that the loss function is convex. You want to minimize the two different parts together. The first is the contrastive loss, and the second is the cross entropy loss. So for the first one, you need to enlarge the distance between the negative pairs. Yeah. So
yes.
How to make sure that?
Thanks for the question. So I think very likely the loss function is not convex. And that is typically the case in a lot of loss functions. And if it's convex, then maybe you can even find a really good solution, like the optimal solution to the loss. But in practice, when we do deep learning, even for a non-convex loss function, gradient descent seems to work really well. And that will still give you a really good solution. This may not be the global optimal solution as is typical the case. If there are problems with, like, if you start from really unlucky starting points, maybe your optimization step will get stuck in some local optima. But we've trained many models in our experiments and we haven't seen such case. And just by measuring the actual distance, we've seen in the final embedding space, they seem to be actually the distance we want. Like we want some distance to be smaller than m, we want some distance to be even as small as possible, and we want some dissimilar distance to be larger than 2m. So to answer your question, I think this is not convex. Very likely it's not convex, but it doesn't really affect our scheme.
Okay, thank you.
Yeah, you're welcome. There was another question from Raymond.
Oh, actually, maybe I can ask the question right now. Since the concept drift will happen over time, so I'm wondering if it is possible that some old training data have negative impacts to the model because some old data may conflict to the new one. Then perhaps it's better to remove some of them.
That's interesting. So in our experiment, we haven't seen such phenomena. I know that in industry, so people have talked about like for Android malware, maybe malware author wants to be stealthy, so they propose a new sample that's doing no bad stuff. Like they would upload a benign looking app. Maybe it's just doing some naive functionality like wallpaper, doesn't do anything for a few months. And then they upload an update to the app with some malicious logic. So this kind of sample is already really hard to encounter in public. And I have no idea how often it is in the wild. But that will require you to observe like conflicting label of a training sample, which, for example, was originally benign and then turned malicious. We have not seen such case in the public data sets we collected. It would be interesting to study cases like this in the future if there's a way to collect such data sets. And I believe there may be even other examples of what would be the conflicting original training sample versus the future sample. Maybe there's a possibility of the other way around. I don't know if a malicious app will actually become benign in the future.
I see. Okay, yeah, thank you.
Yeah, you're welcome.
We're seeing Yizheng just continue, I guess. Yeah.
Okay, sounds good. All right, so we would like to evaluate our new active learning scheme that we combine contrastive learning with active learning. So I'll briefly talk about our experiments and some highlight results. overall, this is the setup for our experiment. We collect multiple years of data from 2 sources. And in both cases, we do the same setup. We train on the first year worth of data, and then we do validation on the next 6 months. We test on the remaining of time period. So we need 6 months of validation, mostly because if you choose a few percent of the validation month to do active learning, the overall percentage of these active learning sample is really small. Like they're definitely under 1% or even 0.1% compared to the original training data. So you do need to do a few months of validation even after you train for 1 year worth of data. And concretely, we collected 2 data sets. One is the hashes from API graph, where they have different sources of malware samples, including virus total, virus share, and academic data set called AMD from previous published paper. They have a total of 320,000 apps spanning from 2012 to 2018. So in this case, we train on 2012. We do validation on the next 6 months in 2013, and our test time frame is over the next 5 years. And then we also collected a new AngelZoo dataset by querying AngelZoo API. So we queried for apps from 2019 to 2021, and we collected a total of 100,000 apps. So in this case, we do training on 2019, validation on the next 6 months, and testing on the remaining 1.5 years. So in both data sets, we follow the previous recommendation from related work to keep 90% of apps to be benign. And we experimented with a monthly label budget of 50, 100, 200, and 400 samples per month. So 200 samples is about 5% of the test sample in the API graph data set. And then I think 50% is about, 50 samples a month, about 1% a month. 100 samples is about 2.5% a month. All right, so we also compared extensively against 6 baselines that have been used in published papers, and 6 improved baseline schemes by using new ideas to improve all the previous schemes or adapt previous schemes like transcend, transcendent, and for active learning. So here is our highlight results. As I've discussed previously in the beginning of the talk, if we just train a fixed classifier and do not do any active learning, you will see many drops of F1 score over time on the right column. And the average false negative rate over the future data of 5 years of test time period for the API graph data set will be 38%. Now, if we do naive active learning for uncertainty sampling, we get about 14% false negative rate. And using our new scheme of a combination of contrastive learning and active learning, we can further reduce that from 14% false negative rate to 9% false negative rate. So if we don't do any improvement over baseline, the SVM classifier with uncertainty sampling is actually the best baseline compared to many other schemes. So here I'm showing another highlight result of actually plotting what would the F1 score be using our scheme versus the best previous baseline SVM with uncertainty sampling. So we further reduce, this is another view of the false of the whole test period evaluation. We further reduce the false negative rate from 14% to 9%. And we also increased the average F1 score from 0.88 to 0.92 over time. So as you can see from the F1 score, the best baseline still experienced more drops of performance compared to our scheme, especially there are a few severe dips of F1 score. We also try to improve the previous schemes as much as possible. Notably, for example, if we apply the transcendent sample selector in our new embedding space instead of the original feature space, it works better than if you just use that in the original feature space. And we also called these improved scheme because they were never documented in previous papers. So here's a short summary of other highlight results. Compared to the best improved scheme, our method reduces the false negative rate by 1.3 times and maintains under 1% false positive rate. So that means that even if we tried our best to use new ideas to improve previous schemes, we still achieved significant improvements in our method. And another result is if we care about maintaining a steady F1 score that is above 0.89, our scheme only needs 50 samples a month labeling budget, but the best previous scheme would need 400 samples a month labeling budget to achieve such 0.89 F1 score. So by this result, we decreased the labeling cost by 8 times to maintain the steady F1 score. And there's one more result. We also use a case study to demonstrate why can we deal with concept drift better than the previous scheme. So here's the view of the F1 score of our method versus the previous best SVM uncertainty sampling method from the middle of 2013 to the end of 2014. So if we look at the F1 score over time, there is a severe drop of becoming kind of the lowest point from the middle of 2013 until June 2014. So in June 2014, both our method and the baseline method has a dip in the F1 score. We looked into the reason why. So there's a new ransomware family called MeCore that suddenly become more popular than before, and both methods misclassify all of them to be benign, which means we have 100% false negative rate just within the family. And because it's really popular, that kind of dominated the performance and explain the reason why our method and the baseline method has such a drop in F1 score. So as this happens, we also looked at what are the samples getting picked up by our method to label. So we show the bars, the green bars, that our method is able to label the MeCore ransomware in June, July, and October 2014. And this allows us to pick up the drift and quickly recover from the dip. As we can see, for our method, we quickly improve the F1 score to make the F1 score back and remain steady over the remaining of 2014. However, when we looked into the baseline method, uncertainty sampling, it never picked up this issue and it never labeled any of the MeCore ransomware family. So for the remaining time of 2014, the F1 score remained low for the baseline method. All right, so this is the end of the talk, and here are our conclusions for this. First, we would like to argue that concept drift is a major problem in security. And it may not be just for malware detection, it's also a problem for many other security applications. In this paper, we showed opportunities to do better than previous schemes. We encourage researchers to study this problem for multiple security tasks. I think there are other opportunities to do this for applications such as PE malware detection, log analysis, network traffic analysis, and maybe there are even other applications you can imagine. Because over time, there are just new malicious behavior and even new benign behavior that gives you natural data distribution shifts, and your old machine learning scheme may not work very well anymore. And I think there are opportunities to develop new techniques to deal with other kinds of drift. So these other kinds of drift may also occur more often in other applications. For example, there can be more gradual drifts. There can even be reoccurring themes of drifts. By reoccurring, I mean maybe the same kind of behavior pattern may reoccur over time. So I've read a recent paper on arXiv on concept drift cellular network traffic. So these researchers measure that because of users' diurnal behavior, we tend to do certain activity during day and then come back the next day, do the same activity. So that will give you some kind of reoccurring themes of drift. So I think there are a lot of opportunities for us to do more work in this research topic. And I hope this talk is useful for us to look more into the concept drift problem. And that's the end. Thank you for taking the time. And I'm happy to take more questions.